Hello everyone and welcome back to your favorite place to be, the Calculus Fun Room. Today we want to take a look at parametric equations, and really over the next two videos we're going to look at parametric equations. And in this video we're going to look at really an introduction to parametric equations, just discuss what they are, how to graph parametric equations. And then we'll finish off the video looking at technology, because that actually makes our graphing a lot easier. We can look at much more interesting curves. But we want to look at kind of the basics, build a foundation here. And in the next video, we're going to look at the calculus of parametric equations. We're going to find slopes of tangents and area under the curve and some other fun stuff like that. So first of all, just kind of the concept here to begin with. We could have a curve in the XY plane, excuse me, and then, let's think about this as like the path of a fly walking on the table. So the fly might land on the table, let's say, at this particular point, and it walks along the curve in, let's say, this direction. So at any particular point XY in the plane, what we really want to think about is at what time, did the bug reach that point. So we want to describe the x location as a function of time and the y location as a function of time as well. And this is what we call parametric equations. So just as an example to start with, let's suppose we take a look at x equals t squared minus 2t and y equals t plus 1. Now, typically the way we want to start a conversation like this is just like we would way back in kind of a beginning algebra course. What does the graph of this equation look like? And the way that we approach that is by plotting points. So what I'm going to do in this case, I'm going to come over here to the left, and I'm going to pick some values of t, and I'm going to find the x and y point that goes with that. And then I'm going to come over here to the right, and I'm going to plot those points in my XY grid. And I'm going to be a little kind of sloppy here with my graphing. I just want to discuss the concept here without being super precise, but of course we could have gridded graph paper. We could be very, very precise as we plot these points. So the t the t value is called the parameter. So t is called the parameter. And what we notice, kind of like we drew up in the graph above, we're not plotting, we don't have a t-axis, if you will. We have an x-axis and a y-axis, and the points are plotted as a function of time. So time is called the parameter because we don't really see that within our graphing plane, but it kind of controls where our x and y values are. Alright, so anyway, let's suppose I pick some points. Let's suppose I pick -3 and -2 and -1, 0, 1, 2, 3. Now, usually, just like in a beginning algebra course, you're going to plot sufficiently many points to where you can kind of see the pattern in what the shape of the graph is. So this should be enough points. If not, we could always come back and plot some more. So I'm going to take x equals -3, and I'm going to plug it into my x equation that I have up here. Right? And then I'll also plug t equals -3 in the y equation. So if I plug in -3 into the x equation, let's see, I'm going to get -3 squared is 9, and then that's going to be plus 6. So x would be 9 plus 6, which is 15. And then if I plug -3 into the y, I get y is -2. So let me say here's 5, 10, and 15 on my x-axis. And let's say here's -1, -2, -3 on my y-axis. And again, I'm just being little non-precise. So x would be 15 and the y would be -2. So my point would be there. And then I would continue this process. So now I'm going to plug -2 for t into both equations. So let's say I'm going to get 4 plus 4, which is 8, and then I'm going to get -2 plus 1, which is -1. So let's see, 8 is going to be roughly there somewhere, and then y is -1. So roughly there's that point. So then I'm plugging -1 into the x, and it's going to give me 1 plus 2, which is 3, and then -1 plus 1, which is 0. So let's say, 3 is about there somewhere. There's that point. and then I continue. So if t is 0, then x is 0. And if t is 0, y is 1. So there's that point. And then if if t is 1, x is going to be -1, y is going to be 2. So let's say -1, 2 is roughly about right there. There's that point. And then if t is 2, let's see, I'm going to get 4 minus 4, which is 0. And then the y value would be 3. Sorry, I got lost on my point there. So x is 0, y is 3. There's that point. And then if x is 3, I'm going to get 9 minus 6, which is 4. No, wait, 3. Oh my gosh, I can't subtract. 9 minus 6. I'm going to do that right. Yeah. And then y would be 3 plus 1, which is 4. So around there somewhere, a y of 4. All right, so I'm kind of seeing a parabola shape here. So let me see if I can sketch roughly my parabola. So if we're kind of interpreting this as, a fly walking on a table, we have a direction in which the fly is going, right? So usually what we'll do on parametric curves is we'll draw, an arrow on the curve to indicate the direction in which we sketched. So in this example, we're just taking a look at, what are parametric equations, right? They're pairs of equations where x and y are described in terms of a parameter, and then introductory conversation, right? If I'm going to sketch that curve, what does that look like? And we're going to plot points to do that. Now let's suppose we have some access to technology and I want to sketch this curve using technology. So on a TI calculator, I'm going to hit the mode key. And you see I'm already in parametric mode here, so I would just go down and turn on parametric mode. And then when I hit the y equals button, we're going to see groups of equations here. So the x equation that we had was t squared. So if you notice your variable button, right, when in function mode it's x, when I'm in parametric mode it's t, if I'm in polar mode it's theta, and if I'm in sequence mode it's n. So when I hit that variable button, it's just going to plug the t in for me. So my equation was t squared minus 2t. And then I could hit the down arrow or enter, and then we had t plus 1 as the y equation. So I'm going to go ahead and hit graph, and let's see what we get. So we can kind of see that parabola that we were getting on our paper, but I'm missing part of the parabola, right? And the reason why is on a TI calculator, if I go to my window button, notice that the Tmin is 0 and the Tmax is 6, and our Tmin in our table was -3 and our Tmax was 3. Now, if we're not told to restrict the parameter, technically it goes from -infinity to infinity. I'm going to do -10 to 10 because that should give me plenty of points on the graph to really see the shape. So let me go ahead and graph there. And you notice when it graphed, it very quickly went in the direction that we denoted. Right? And one thing we could always do is we could hit trace, and notice that the trace puts the parameter value in there. So as I start to hit the right arrow, it's going to trace as the t increases. And of course, we're way off the screen here. So let me just jump to -3. We say -3, hit enter. And then now I continue going to the right, as the parameter increases. And we can see, here's my cursor, and we can see the points being plotted in that particular direction. Now, if I go to the table, let me do second graph and go to the table, we can see, for values of the parameter, here's the x and y values, and as you guys definitely know by now, if I do a second window that takes me to the table setup menu, I could start my table at a particular point. I could have my delta t. In that case, I could always go down to the ask feature. And if I go back to the table when I do that, I could plug in t equals -2.5, let's say, right? And it's going to plug into the equations and find that value for me. Now let's suppose we have access to graphing technology, maybe like desmos.com. So notice what in Desmos, right, what we have to do is type an ordered pair, right? So I would hit left paren, type my x equation, comma, type my y equation, right, and then close off my right parenthesis. And then notice that Desmos does a 0 to 1 for my parameter, so I'm going to do minus 10 to 10, and I can see the graph there in whole if my domain was minus infinity to infinity for my parameter. Now, in applications, a lot of times what t will represent is a time variable. So we don't always see t being negative. We'll sometimes restrict the parameter for a specific interval. So if I take this example and I restrict my interval, so let's suppose we look at x equals, and I'm going to leave my table here. Let's look at a slightly different example. So let's suppose we look at x equals t squared minus 2t and y equals t plus 1, and let's say we're going to restrict t to go from 0 to 3, let's say. Now I'm going to use the table above just to kind of cheat, and I already had those ordered pairs that were there. So if t is 0, I was at the point 0, 1. And if t was 1, I was at the point negative 1, 2. And then if t was 2, I was at the point 0, 3. And then if t was 3, I was at the point 3, 4, let's say, something like that, right? So again, we're starting where t is 0, and then we're tracing in that direction. So we still have a particular direction that we're tracing. Now let's, I've been using the fly on the table, and if we think of the fly lands at 0 seconds and walks until 3 seconds, and then, takes off, gets off of the table, right at t equals 0, right, that's our initial point. So a lot of times in a physics class, we'll consider the variable time, right, for the parameter, and my initial point in this case was 0, 1. And then in this case, right, my example, I picked t equals 3, and that's our terminal point. And so that's where our graph ends. And in this particular case, that was 3, 4. Now, another really fun example to look at that we will typically see in a calculus textbook is some circles and ellipses. So one of the I guess I want to say advantages of parametric equations, if we look at these two graphs, here's a graph that is not a function of x. Right, so what would the equation look like if I what we call eliminate the parameter? So what if I get x and y's in an equation instead of x a function of t and y a function of t? Now this isn't always possible to eliminate the parameter, but usually the first couple problems in a calculus book of this level will give you some simple parametric equations so that you could eliminate the parameter. So before we go look at the fun stuff that's more intricate, let's take a look at eliminating the parameter here. So for this same example, let's eliminate the parameter to obtain a Cartesian equation. All right, now again, a Cartesian equation would involve only x's and y's. And this isn't necessarily going to be y as a function of x, and in this particular case, y isn't a function of x. So think about how we might do this, right? And probably the simplest way in this particular example is I'm going to do substitution. So I have the equation x equals t squared minus 2t, and I have the equation y equals t plus 1. So I'm just going to substitute. So if I solve for t in this equation here, t is y minus 1, and I'm going to substitute that into my x equation. So my t is y minus 1. And technically, here is my Cartesian equation. So I have x as a function of y, and that's my Cartesian equation there. Right? And I could FOIL all that stuff out. Usually in a calculus textbook, that's probably what you'd see in the solutions manual. So we would write this as y squared minus 2y plus 1 minus 2y plus 2. So x equals y squared. What's that going to be? Minus 4y plus 3. So this would kind of be our final answer typically. All right, so there's a Cartesian equation. Now again, notice x is a function of y. Y is not a function of x. All right? And again, if you think about, converting the graph, kind of flipping it on its side, right? We have the graph passing the vertical line test where x is a function of y, right? In that case. Okay, now let's get to the fun stuff where we look at some circles. I'm going to leave that there for a moment, right? And where we take a look at some circles. So let's take a look at another example. So in this case, what I want to do is let's consider the parametric equation where we have x equals cosine t and y equals sine t. And then let's eliminate the parameter to be between 0 to 2 pi. Now, for this particular example, right, the reason I'm eliminating the parameter for the moment for our conversation, if you think about cosine and sine, they're periodic. So cosine is going to run through all of its possible values from 0 to 2 pi, and then it's just going to start to repeat itself, and ditto for sine. So if we take a look at this graph, I could build a table and plot points. I'm not going to bother to do that in this case. Well, you know what? Let's go ahead and plot a couple points. Right? Just remind ourselves of what this would look like, and then we're going to lean on some technology. Now, if I'm going to pick values of t here, I want to pick values of t that make things as easy as possible for me. And what I mean by that is I'm going to pick, 30, 45, 60, 90 types of angles. So if I pick, let's say, pi over 6, right, 30 degrees, and man, I always forget what these are. I could look at my unit circle, but I always memorized these two reference triangles. That's not a good sketch of a 45, 45, 90, right? So smallest angle of 30 has smallest side opposite of 1, and then 2 and square root of 3, and then 1 and root 2 on my reference triangle. So if we look at pi over 6, that's 30 degrees. So the x equation is cosine of pi over 6, and the y equation will be sine of pi over 6. So if I look at cosine of 30 degrees, that's adjacent over hypotenuse. That's root 3 over 2. And if the y would be sine of 30 degrees, which would be opposite over hypotenuse, and that would be 1/2. So I'll come back and plot these points in just a moment. So if I look at pi over 4 next, so that's 45 degrees, right? Sine and cosine of pi over 4 are 1 over root 2, which sometimes we could rationalize that as root 2 over 2. And then if I look at 60 degrees, pi over 3, so cosine of 60 is adjacent over hypotenuse, which is 1/2, and then sine is root 3 over 2. So I just wanted to pause the video for a second, take out my calculator and get some decimal approximations to those values, and then I plotted those points on a very rough, dirty sketch of an XY grid. And something I forgot to do, I want to go ahead and do, is let's pick t equals 0, and then let's pick t equals pi over 2. So if I plug t equals 0 and pi over 2, right, the way I think about this is kind of on my unit circle. Remember, on the unit circle, you have cosine theta and sine theta as the points on your unit circle. So the x value is 1 and the y value is 0 when theta is 0 radians. So I would have the point 1, 0 here, which would be that point there. And then when I'm at pi over 2 radians, I'm at the point 0, 1. So there would be that point there. So if we were to continue plotting points, which I don't want to take the time to do, we would end up getting a unit circle. Well, mine's not exactly a circle, but something roughly like that is what we would get here. And again, this shouldn't be too surprising based on what I drew over here on the right. Right, I drew the quadrantal points on the unit circle to help myself find the values of cosine and sine. So as t varies, in this case, it's almost like t is playing the role of the angle theta. And we could think of theta as the parameter over here on the right, where t is the parameter in our set of equations. So let's take out some technology and just graph that to see what that looks like. So if I bring out my TI calculator, I'm going to hit the y equals key, and let me do x equals cosine of t, and then I'll do y equals sine of t. And then if I go ahead and hit graph, we're going to see our circle there. And it doesn't really look like a circle. So I want to fix that to look like a circle. Also, we had graphed in our last example, like we let the parameter be minus 10 to 10. So I'm going to go into the window here, and I'm going to go from 0 to 2 pi, which is what we specified in this problem. So let me fix that. We'll go 0 to 2 pi, and now when I graph, we see that circle again. Now the reason that I had done that was, let me hit trace, where's my trace key, and we see that we start at the point 1, 0, and then as t varies, we see the point trace counterclockwise, just like we would plot our unit circle as theta goes from 0 to 2 pi. Now when we get to 2 pi, we stop here. So we only trace the circle one time in a counterclockwise direction. Now if we bring up desmos, I'm going to do the same thing. I'm going to write an ordered pair using t as my parameter, and then I'm going to go from 0 to 2 pi here as well. I'm going to do 2 times pi, and we can see there's that unit circle on desmos as well. So if we just want to give a little description of our curve here, right? So this curve, the curve was traced. I want to say the curve, parametric curve traces the unit circle starting at 0, 1, counterclockwise. My fingers don't want to work today. They hardly ever want to work. Counterclockwise. And ending at 1, 0. Uh-oh, and there's another typo I had there. We started at 0, 1. We started at 1, 0 and ended at 1, 0. So I'm going to come back up here and put an arrow on my circle and just point out to myself the direction that I sketched. Now one thing in terms of the language within a calculus textbook, well, I want to point out to ourselves that usually up to this point we've used the term curve to represent a graph in the xy plane. So really our curve is the unit circle. The parametric curve, right, we use the term parametric to designate that we really are looking at like a particle that travels along a curve in the xy plane. So the parametric curves, the term parametric curves implies that we're looking at a point that moves in a particular direction as the parameter increases. Now let's suppose, this was a problem in the book and we want to eliminate the parameter. And again, I mentioned to you we don't always do this, but let's suppose that I wanted to, right? I have an equation, or excuse me, I have a graph, a unit circle. I know the equation of any circle basically is x squared plus y squared equals r squared. Now, so any circle, let's just remind ourselves, has the Cartesian equation. I'm going to say x minus h quantity squared plus y minus k quantity squared equals r squared. So remember in that form, the center was hk, right, and the radius was r. Okay. Now in this particular case, we are centered at the origin. So I'm going to have, x minus 0 squared plus y minus 0 squared, and my radius is 1. So for this particular example, we should have x squared plus y squared equals 1 squared, or just 1. Now how would we make the connection to the parametric equation? So I'm going to write back down here. I'm going to pick the color red. So we had x equals cosine t and we had y equals sine t. So the way we would make the connection here, this isn't going to be algebraic. So in that prior example, we solved for t and plugged into the other equation. And I don't want to do that in this case. What I'm going to do is I'm going to use the identity, the Pythagorean identity technically from a trig class, right? We know that cosine squared of t plus sine squared of t is going to equal 1. And now I'm going to do a substitution, if you will. So the x, I'm going to highlight in yellow, the x is cosine t, right? So I'm going to replace cosine with x. Now I'm going to take an extra step here, right? We typically think of cosine squared plus sine squared. We write in a more efficient manner as we did in that first line, right? But that's really what it is cosine, quantity squared, sine, quantity squared. So I'm replacing the cosine with x, just like I did where I highlighted in yellow. And I'm replacing the sine with y. Oops, I'm replacing, my mouth said sine, my hand wrote sine. So there's our x squared plus y squared equals 1. So typically in homework problems within a section like this, you'll be asked to eliminate the parameter. If the equations are trigonometric, we're going to connect to a known identity. If the equations are polynomial like we had up here, we're going to do basically like an algebraic substitution like we did in that first example. Now, a lot of problems in an introductory section like this, having a conversation about parametric equations, we'll take a look at circles, ellipses, and hyperbolas in particular. In a couple videos from now, we're going to take a look at those same graphs, those conic sections, in polar form. But first, how would we do the parametric version for any particular circle? So if we come back and we think about that generic form of the circle, and what we're trying to do is connect to, sine squared, or I think the way I wrote it above was cosine squared t, and I'm going to write it that other way that we did above, cosine squared plus sine squared equals 1. Now, when we look at our circle equation, we have equal to r squared, and what I want is equal to 1 over there. So I'm going to divide everything by r squared for my circle equation. And then that way I can make the connection to my identity. And then I'm going to also take one more step and write this as like x minus h over r quantity squared and y minus k over r quantity squared equals 1. So now I can connect to the sine and cosine identity, right? So what's in the parenthesis, cosine, has to equal x minus h over r, and then the sine has to equal y minus k over r in order for us to get that parametric form. So I would have x minus h over r equaling the cosine t, and y minus k over r equaling the sine t. So just a little bit of algebra here. I'm going to multiply both sides by r, and then I'm going to add the h, and then I'm going to multiply both sides by r, and then add the k. So this is my general form of a circle with center hk and radius r. So usually what I like to do in my class at this point is give a fun little activity where I ask you to group in pairs and sketch a smiley face for me. So what I want you to do for your smiley face is bare minimum give me a outer perimeter of the head and give me 2 eyes. Now, I also challenge students to give me a mouth, like maybe a smiley face or a frowny face or, a surprised face or whatever it is you want to do. I've had some students put ears. Some students put like 2 little sprouts of hair on the top. So I want you to pause the video for me, and I want you to take out your technology. I want you to try, doing equations of circles with that generic form. You're going to have to shift the circles left and right and up and down to get the eyes, and play with the radius to get them large and small. So pause the video, see if you can draw a smiley face with your technology, and then when you're done, unpause the video, come back, and I'll show you what I did. Alright, so how did you do? How did your smiley face come out? Well, I wish I could see them. That's one thing I love about walking around the classroom is I can check out smiley faces, and I'll grab a couple calculators and come up and put it under the dot cam and display for everyone. So here's my smiley face. So as you can see, I basically did 3 different circles, one for the big face and the 2 small eyes, and then I did 2 different parabolas. Now when I first did those parabolas, they graphed way too far, because remember, under the window I'm going from 0 to 2 pi here. So what I was doing, I did like y equals t squared, x equals t, and it gave me a huge parabola. So I had to play around with the coefficients, right? The vertical shifting of those coefficients. And then I subtracted 3 to move them down to start at 3. Right. Now, because I was doing x equals, 0.5t, and the window was 0 to 2 pi, I wasn't getting any negative x values. So I just went ahead and did it this way. Now there's a lot of different ways to do that face with the mouth. Some people like to do a frowny face and some other fun stuff. I've had some students put pupils, little circles inside of those eyes. Now something I meant to mention earlier is when you graph a circle on the TI, this should look like a circle. We know these are circles. So because I'm going from -10 to 10 on the x, -10 to 10 on the y, look at this viewing rectangle, right? It isn't square. It's so the x's are being stretched horizontally to fill up that window. So what we can always do is go zoom, and zoom square, number 5, will square the window for me. So notice it doesn't go -10 anymore. It goes a little further out to kind of squish in the x's and get a truly square window. In fact, if we go to the window, we can see now that our x-min and x-max are about -16 to 16. So I hope you had fun with that. That was a lot of fun. I want to take a look at one more example here. And before we do the last example, I want to take a look at a couple really fun graphs that Stewart's textbook, I'm pulling up Stewart's calculus textbook here, that he puts in his section. So if you look at these equations, these look very simple, right? X equals t plus sine 5t, y equals t plus sine 6t, and you see this really funky graph that you get here. So this graph is way far away from being a function in the xy plane, and we can see that some relatively simple parametric equations can describe that shape. If we take a look over here at another example that he has, again, 2 equations, or I should say a set of parametric equations that looks quite simple. X equals sine 9t, y equals sine 10t, and we get that graph. And then the last example he has here is equations that look a little bit trickier, right? And they give us some kind of this like spirograph here as well. Now, one application, there's more than one application to parametric equations, but one of them is laser printing. So there's some laser printers that use parametric curves to sketch letters. In fact, another fun activity I used to do in class was, instead of sketching a smiley face, come up with sets of equations to sketch the letter C. And that one's pretty simple because it's basically a circle. There's only a portion. And then like sketching the letter S and the letter T. So you have to use multiple sets of equations to sketch a T, because you really have 2 pieces of graph to deal with. The last example I want to take a look at is an application where we look at projectile motion. Now we're going to look at this example, projectile motion in the 2D plane, and in a calculus course, usually in Calc 3, you'll take the next step and you'll look at graphing curves in the 3-dimensional plane, and there are scenarios where it will be simpler to sketch a curve, trace a curve in the 3-dimensional plane using a set of parametric equations. But for now, we're going to keep things in the 2-dimensional plane. And so here's kind of a physics example where if we have a projectile, so I'm posing an example that a gun fires a piece of artillery at an angle of 30 degrees. So here's our angle of 30 degrees. And then our initial velocity is 500 meters per second. So if I plug into my projectile motion equations here, I have the coefficient of t being 500 cosine 30 degrees, and then the coefficient of t in the y equation and then minus 1/2. So g is the acceleration due to gravity. That's 4.9 meters per second times t squared. Now we can actually derive these equations relatively simple using Newton's laws of motion, right? Acceleration and gravity being constant at 4.9, or excuse me, I should say 9.8 meters per second squared, which I have written wrong there. Let me fix that. G is 9.8 meters per second squared, or 32 feet per second squared. So here's my two equations, and we could derive this relatively easy with some trigonometry. If we think of kind of the velocity vector, if you will, we're looking at a triangle there with 30-degree angle measure, and we could relatively easily find the x direction of that vector and the y direction of that vector and derive these equations. For the sake of time in this video, this isn't a physics class. I'm going to skip over that derivation and let's jump to this application. So for this particular scenario, here are our parametric equations, and I know that cosine of 30 degrees is, what is that? And that's square root of 3 over 2. So I have 500 square root of 3 over 2 t, which obviously that's going to be 250 root 3 t. And then the y, so sine of 30 is 1/2. So that's going to be 250 t minus, and half of 9.8 is 4.9 t squared. So here's my two equations of my projectile motion. Here's my x equation, and here's my y equation. So usually in a class of this nature, we're given that information, we're not being expected to derive those sets of equations, and we're asked some applications. And probably one of the first questions you would typically see, how far does the projectile travel from its launch? So let's say part A is how far does the projectile travel? Now in this case, what we really mean is horizontally, right? So we just want to look at the travel horizontally from launch. All right, now in this case, if we come back up and look graphically, right, where the projectile lands, it has a height of 0. So I'm going to set my y equation equal to 0 here. And that's going to find vertically when it is resting on the x-axis. To save a little bit of time, I paused the video. After setting y equal to 0, I went ahead and factored out a t, and then I set each factor equal to 0. I got t equals 0, and we got 250 minus 4.9 t equal to 0. So the t equals 0, the height is 0, right? And that's obviously before we ever launch the projectile here at the origin. And then we get approximately 51 seconds, which is where it's going to hit the ground out here. Now the question was, how far does it travel horizontally, right? So that's our x distance. So my distance would be, I'm plugging 51.02 back up here into my x equation, and I'm getting approximately 22,092 meters. I brought up Desmos and graphed the two parametric equations that we had, just so I could envision, right, the graph. I went from 0 to 52, so I should be able to do like 51. I can see that visually checks what I'm looking for there, and it looks like that's about 22,000. Seems to be matching the answer that we got. The last part of this problem I want to take a look at is a question that says, what is the maximum height that the projectile obtains? Now, if we think, I want to try to animate what this would look like, right? If we think of our projectile starting here, it launches up and falls back and lands. It's supposed to be a parabola there. Now, if we sort of separate our coordinates for a moment. So as time progresses, the x equation that we have is giving me the distance that we're traveling horizontally. So the derivative of x over time is telling me the speed at which I travel horizontally. If we think similarly, the y equation, right? The y equation tells me the speed at which I travel vertically. So if I think of dy dt, that gives me the speed. Excuse me, I think I said that wrong, right? Y tells me the height as a function of time. So dy dt tells me the change of height as a function of time, right? Change of height per unit time. So if I think as I travel vertically, right, when I hit that max peak, my y rate of change becomes 0 right at that moment, and then I travel back down as I pick up speed. So when I hit my max, I'm really looking for where does the change of y per unit time become 0. So if I come back up and look at my y equation, where was my y equation? There it is, 250t minus 4.9t squared. So I got 250t minus 4.9t squared, and I'm finding when the change of y is 0. So very quickly, I get 250 minus 9.8t being equal to 0. And then if I solve for t, I'm going to get that value there. Now if I plug that into a calculator, I get about 25.5 seconds. Now that should make sense because in this problem we had about 51 seconds where we hit the ground, so about halfway between there I should reach my max height, right? Without any wind resistance, that should be the case. Now, I believe this question said, what is the maximum height, right? So we're going to need to plug that value back into my y equation and find out what that max height is. I'm getting about 3189 meters. Okay, that's the last example that I wanted to do with you here. This is a little bit of foreshadowing of what we're going to do in the next section. The next video is going to be calculus of parametric curves. So we're going to find slopes of tangents, areas under the curve, arc length, and even surface area. All right, so I will look forward to seeing you in the next video.